Greetings of the day, dear students. Welcome to the basic electrical and electronics engineering class. In this video, one of the important topic, full wave rectifier with the center tap connection, we are going to discuss. By the time we complete this video, we are going to discuss its circuit diagram, what are the different waveforms we are having, and also we will discuss its operation and the analysis part, how to calculate the DC or average output current, and also we will calculate the average DC output voltage, RMS output current IRMS, and also RMS output voltage VRMS, and the rectifier efficiency eta, right? And we will see the peak inverse voltage, form factor, peak factor, all those things we are going to discuss in this video, right? Dear students, with respect to the full wave center tap connection, rectifier with center tap connection, we are going to have two diodes, diode D1 and diode D2, right? And a transformer with its primary and secondary. And this full wave rectifier is going to convert the AC voltage into the pulsating DC voltage using both the half cycles. So how do you understand that? For example, in these two diodes, during during positive half cycle of the input, diode D1 will be in the forward bias state and diode D2 will not be conducting. So here the current flows through the diode D1 onto the load resistor RL during the positive half cycle. The current flowing through the diode, you can observe here in this waveform, it is going to conduct within the time period 0 to pi. Now, during negative half cycle, within the time period from pi to 2 pi, the diode D1 will be reverse bias and the diode D2 will be forward bias. The diode D2 will be forward bias, and during negative half cycle, right, this diode D2 is going to conduct and current flows to the load resistor RL. So during pi to 2 pi, now the diode D1 is in the off state, no current flows through the diode. At the same time, during that period, during pi to 2 pi negative half cycle period, now the diode D2 is in conduction mode. There will be the conduction and the current flows through the diode. And if you observe during positive half cycle within the 0 to pi, the diode D2 is not conducting. Like this, the process get repeated. Again from 2 pi to 3 pi, diode D1 will be conducting and diode D2 will be in the half state. Like this, at any point of time through the load resistor, the current flowing through the diode load resistor will be in this manner. It will be 0 to pi, it is existing, pi to 2 pi also it is existing. Like this, we are going to get the current through the load resistor RL. Right now, this the purpose of this center tap transformer is it is going to produce two sinusoidal waveforms of same amplitude and frequency, but those waveforms will be out of phase with respect to the ground secondary winding. So this is about the circuit operation. Dear students, I repeat again, the important point during full wave rectifier with center tap connection is at any point of time the current will be flowing through the load resistor RL, right? Now during positive half cycle, diode D1 will be in the forward bias state, and during negative half cycle, diode D2 will be in the forward bias state, right? So now this is all about the operation. So it can be observed that load current flows in both the half cycles. Coming to the analysis part, you are going to calculate now so many parameters: average value or DC value, RMS value, form factor, peak factor, and the efficiency. All those things we are going to calculate, right? For all those things, the basic input is of sinusoidal in nature, and its mathematical representation is V input. Vi of t is given by Vm sin omega t. If you are having a waveform like this, sinusoidal waveform, right, and this value, this is the Vm, right, this is sinusoidal in nature, so it is represented Vi of t equals to Vm sin omega t. Now the current I1 through diode D1 and the load resistor RL and through the load resistor RL, it is given by, let that current value be I1, it is Im sin omega t. If we observe the previous waveform, it is existing with 2 pi and pi to 2 pi, again it is 0, and again from 2 pi magnitude. So this is the current through the diode D1, and we have represented with the variable current through the diode ID1. So that is what we have written here. Its mathematical form within the time period 0 to pi is Im sin omega t, and within the time period pi to 2 pi is 0. Very important. Within the overall time period of 0 to 2 pi, it is again divided into two parts. One is within the limits 0 to pi, and the another one within the limits pi to 2 pi. Now here the Im represents what? Im is equals to the Vm divided by Rf plus RL, where Rf indicates the diode forward resistance and RL indicates the load resistance. RL indicates what? RL indicates the load resistance and Rf indicates the diode forward resistance. Similarly, the current through the diode D2, within the 0 to pi period there is no magnitude of current flowing, and but within the time frame during negative half cycle from pi to 2 pi there is a magnitude of current is existing. So this is the current through the diode D2 I D2. So we can write it as I2 equals to, within the limits 0 to pi its magnitude is simply 0, and from pi to 2 pi its mathematical form is Im sin omega t. Im sin omega t. Clear? So this is the first part. Current through diode I1 and current through diode D2 is I2. Within the limits 0 to 2 pi, better split it into two parts. 0 to pi is one part and pi to 2 pi is one part. During positive half cycle in diode D1, within the limits 0 to pi, Im sin omega t. Within the limits pi to 2 pi, 0. Right? Now, through the load current through the load resistor RL will be what? It is the sum of both. It will be the sum of both the currents. So it is simply I1 plus I2. Now the current flowing through the load resistor is I1 plus I2. That is that is one more important point. Current through the load resistor IL is I1 plus I2. Now what about the DC component? If any waveform is given, right? If you are asked its average value, what we will do? We have to take its integral within the limits 0 to time period, and if you divide with 1 by t, we used to get the time period. We used to get its average value for any given waveform. If you are asked to calculate its average value, simply you take the integration of that waveform within the limits 0 to t and divide with 1 by t. That is what we are going to do here. Now I of t in mathematical form we can express 1 by t 0 to t I of t dt. In this context the time period t is 2 pi. So 1 by 2 pi within the limits 0 to 2 pi. Now this I of t is going to consist of two parts, just we have discussed here. I of nothing but I1 plus I2. So that is what we have written here, I1 into d omega t plus I2 into d omega t. So again this I1 of t, from our previous assumption, previous analysis, we can observe it is again written in terms of two parts. 0 to pi you are having the magnitude Im sin omega t. Within the limits pi to 2 pi its magnitude is 0. So for I1 of t it is completed. Coming to I2 of t, 0 to pi its magnitude is 0 and pi to 2 pi Im sin omega t. So if you take integral of sin omega t is nothing but minus cos omega t within the limits 0 to pi. Im is constant, we can take it outside. Integral of 0, this is 0, and this integral of 0, this is also 0. Again integral of sin omega t with respect to d omega t. Integral of sin t with respect to dt is nothing but minus cos t, right? So that is what we are doing here. Integral of sin omega t with respect to d omega t minus cos omega t, but the limits are pi to 2 pi. Now if you take out Im common, what about cos pi? Minus 1, minus of minus plus 1, cos 0, 0, minus of minus, upper limit minus lower limit, upper limit minus lower limit, minus of minus 1 minus cos 0 is 1, right? So minus of minus is there, no, plus 1 we will get. So here we used to get 2 Im plus, again for this term also we will get 2 Im. So overall it is 4 Im by 2 pi, which is further simplified to Im by pi, which is nothing but 0.318 times Im. 0.318 times Im. This is very important. So dear students, the average value in a full wave rectifier with center tap transformer IDC value is how much? 2 Im by pi. 2 Im by pi. This is the IDC value. Once we know the IDC value, right? Already we know the Im value. Im equals to how much? Vm divided by Rf plus RL. So IDC equals to 2 by pi Vm by Rf plus RL. Rm, this is important. IDC equals to 2 by pi into Vm by Rf plus RL. Similarly, once you know the current, we can easily calculate the voltage. What will be the voltage? Simply V from Ohm's law we know V equal to IR. We know the DC current. So VDC will be IDC into the load resistor value. In this context it is RL. So VDC equal to IDC into RL. IDC just now we have calculated 2 Im by pi into RL. So it is 2 by pi bracket of Vm by Rf plus RL into RL. In case, of course, most of the times if the load resistor value is very high compared to the forward resistance of the diode, we can neglect the RF value. So what happens? It is simply if RF is neglected, RL by RL will get cancelled, right? So VDC equals to 2 Vm by pi. VDC equal to 2 Vm by pi. Very important. This is also important. Yeah, so two important points we have calculated: IDC and also VDC. Keep in mind, dear students, this is for full wave rectifier, half wave rectifier, full wave rectifier, and bridge rectifier. For all those three things, what are all these values? We can summarize in the last video. Right? Yeah. Now, RMS value, root of mean of the squares of what? RMS value of just observe, you have taken the square root of the average value of the squares. Square of what? Current. I square of t dt. I square of t dt within the limits 0 to t 1 by t, sorry, with this integral of 0 to t I square of t dt into 1 by t, and we will take square root for that one, right? So now we will have, already we know the from the previous basics, its mathematical form is I of t is how much? Im sin omega. The mathematical form is Im sin omega t, but we are supposed to take I square of t. So what happens? Im square sin square omega t with respect to what? Derivation, derivative of omega t, right? Now sin square theta, from trigonometric basics, sin square theta equals to how much? Sin square theta, sin square theta, how we can write it? Equals to 1 minus cos theta by 2. Sin square theta we can write it as 1 minus cos 2 theta by 2. That is what we have done here. Very simple. We can take out Im square common. So Im square by 2 pi is taken out common within the limit 0 to pi. Within the limit 0 to pi. Now sin square theta we have written it as 1 minus cos theta by 2. So 1 minus cos 2 omega by 2 omega t by 2. The derivation is with respect to what? Omega t plus pi to 2 pi. Here also sin omega t we have written it as 1 minus cos 2 omega t by 2 into derivative of omega t. But what about Im square by 2 is also taken out common. Im square by 4 pi, right? Derivative integral of 1 with respect to omega t. Integral of 1 with respect to what? Omega t. So we will get omega t. But what are the limits? 0 to pi minus integral of cos 80 minus sin 80 by a, right? So we will get sin 2 omega t by omega within the limit 0 to pi plus, similarly for the pi to 2 pi limits also, integral of 1 we will get omega t, and integral of cos 2 omega t with respect to d omega t we will get minus sin 2 omega t by omega t within the limits pi to 2 pi. If we further simplify this, keeping the upper limits and lower limits, this is what we will get. Pi square by 4 pi minus 0 minus 0 minus of 0 plus 2 pi minus pi 0 minus of minus 0. So if you further simplify, 2 pi minus pi, you used to get pi, and here one more pi is there, pi plus pi 2 pi, im square by 4 pi into 2 pi. If you further simplify, root over im square by 2. So root over im square by 2, it can be simply written as IRMS equal to Im by root 2. Very important. The root mean square value in a full wave rectifier. So IRMS equals to, if its value is Im by root 2. For example, if I have a waveform like this, if you whose for example its value is 1, peak value is 1, then the RMS value will be how much? 1 divided by root 2. What about root 2? 1 divided by, what about 1 divided by root 2? 1 divided by root 2, 0.707. 0.707. If it is 100, we may get, for example, if it is 100 amps, okay, 100 by root 2 we will get, so 70.7 amps we will get. So if it is 50, and again half of that, so that much component will be the IRMS value. RMS value is how much? 70.7. If peak value is 100, like that we have to understand, right? So the RMS value is how much? Im by root 2. Similarly, with respect to the voltage, Im is what about the current? Im is nothing but Vm divided by forward resistance of the diode plus RL. That is what we can substitute here. IRMS equals to Vm divided by root 2 into RF plus RL. Now, if forward resistance of the diode, if it is very less compared to the load resistance, then VRMS also will be how much? Vm by root 2. Very important. Very important. VRMS equals to how much, dear students? Vm by root 2. So 4 major parameters are completed: IDC, VDC, IRMS and VRMS. If you recollect, IDC, how much we got? IDC is it 2 Im by pi, 2 Im by pi, 2 times Im value by pi we got. So IRMS, how much we got? IRMS is Im by root 2. For VDC also we have calculated, and also VRMS. 4 major parameters for full wave rectifier are calculated. VRMS, how much we got? Root 2. When if the forward resistance of the diode is very less than resistance, right? Now let me discuss about the efficiency. Another important parameter is the efficiency. So here the efficiency is defined as the ratio of DC output power to the AC input power, P divided by PAC. And now already we know the PDC, nothing but I R. The power P is nothing but I square R. It is or I square R or V square by R. Anything is okay, right? So here I square R, but in this context the current is IDC square into RL. IDC just now we have calculated 2 Im by pi. So IDC square 4 Im square by pi square into RL. Now what about AC component? RMS value IRMS square into the resistance RL plus RF. So IRMS is nothing but Im by root 2, but here IRMS square is there. So Im by root 2 whole square, Im square by 2 you get into RL plus RF. That is what you will substitute here. In the place of PDC, 4 Im square by pi square into RL whole divided by, in the place of PAC, Im square by 2 into RL plus RF. It is around 8 by pi square into RL by RL plus RF. If you further simplify, if you take out RL common, it is around 0.812 whole divided by 1 plus RF by RL. Very important. In terms of percentage, if you express, it is around 81.2 divided by 1 plus RF plus RL. This is the efficiency for full wave center tap, full wave rectifier with center tapped connection, full wave rectifier with center tapped connection, right? So this is the efficiency. Next, the peak inverse voltage, how it is defined as? The peak inverse voltage is the maximum possible voltage across the diode when it is reverse bias. when the diode is reverse biased, what could be the maximum possible voltage across the diode? For example, if we consider the diode D1 is forward biased conducting and diode D2 is reverse biased, that is not non-conducting. In this case, what happens is Vm is developed across the load resistor RL. Now the voltage across the diode D2 will be what? It will be the sum of the voltages across the load resistor RL and the voltage across the lower half of the transformer secondary. Because of that, what happens? The peak inverse voltage for diode D2 will be already Vm is existing. Vm plus Vm, it will be around 2 Vm. It will be around 2 Vm. So the peak inverse voltage will be how much? 2 times Vm. Now what about form factor? It is defined as the ratio of RMS value to the average value. Ratio of RMS value to the average value. RMS value just now we have derived Im by root 2. Average value 2 Im by pi. So it is 0.707 Im whole divided by 0.63 times Im. It is around 1.12 for full wave rectifier with center tapped connection. So for the form factor is 1.12. What about peak factor? Peak value divided by RMS value. Peak value is Im. RMS value is Im by root 2. You will get it as root 2. So it is 1.414. 1.414 is the peak factor. Peak factor. 1.414 is the peak factor. So the form factor is 1.12. Right. So these are all the important points with respect to the full wave rectifier. Clear? So these are the things, dear students. Uh, these are all the important points, and the main thing is the in a full wave rectifier during positive half cycle diode D1 is conducting and during negative half cycle diode D2 will be conducting. At any point of time the current through the load resistor will be existing within the limits, uh, whether it is 0 to pi or pi to 2 pi, right? So here from this waveform, during forward bias mode of the diode D1, only the current flows within the period 0 to pi, and pi to 2 pi it is 0. Similarly for diode D2, during positive half cycle it will be reverse bias, no current flows 0. During negative half cycle there will be the conduction within the limits pi to 2 pi, right? And this is the center tap transformer. This is the input waveform which is to be rectified, and this is the rectified output. If you use filters across the output, then we can get a eliminate or remove the ripples. Ripple content can be removed, and if any AC components are present, those can also be filtered out with the help of the filters. So this is about the full wave rectifier. Thank you.